antimatter
Uh-huh.
uh, and
Okay.
accumulations of antimatter and disrupting like
A-
different parts of space time or something like that.
And I think I probably allayed your fear, or just you come back for some more.
No, you laid my fear on that one.
Okay.
It was a while back, but I'm
Okay.
good on antimatter. But
Good.
uh,
No, no antimatter fears left. Okay, good.
so my question was, why are neutrons neutral? Now, I don't know if this is necessarily astronomy, if
No,
but
that's fine. That's a good question. And
because I'm skeptical if like I guess my full question would be I'm skeptical to think like have we prematurely dismissed the neutral nature of neutrons and there actually is more there than it just being like yeah it's like okay yeah there's like these neutrons but let's go over to electrons and protons and talk about those two like why are neutrons just kind of skipped over. Yeah, okay, that's my
yeah, I
question.
skipped over in terms of, I mean, they're not skipped over. They're part of they're definitely part of the party for protons, neutrons, and electrons. I don't know what you mean by skipped over,
Well, I guess like they're shown as having like no charge.
which is true.
That's the behavior of it. And I guess protons are the names of the atoms, and then the electrons are like their outer orbital shells, like how the columns get lined up and whatnot. But
Kind of, yeah, yeah, yeah. Protons are the guys in charge of the atomic number, and basically there are 92 ones that are familiar to and basically exist commonly on the planet. 92 different ones, determined entirely by how many protons. But you can have uh, a uh, uh, a fair amount of extra neutrons depending on how big a number of protons you have. So uranium has, I think there's uranium 238, I believe, and if you subtract 92 from that, you'll get the number of neutrons left. But they're all neutral. They do not have charge. They have, they're composed of quarks. And have you heard of quarks?
right, that's what's this field of study? Like theory, like string theory or not string theory, but go on. I can't remember it right now.
Okay, so the weird thing is that a proton has a charge of plus one, an electron a charge of minus one, but a proton, and this is where I'm a little bit shaky in terms of the way it adds up. A proton has a charge of plus one, but it's made up of three quarks, and each of them are made. Their charge is either one third or two thirds, and they add up to one. So let's say you have a plus two thirds and a minus two thirds and a third. No, that doesn't add up. How about two, uh, two plus two thirds and a minus one third? And together that creates a plus one. So and that is a proton made up of three quarks. A neutron, believe, because this is not my expertise, but because I keep forgetting it. I've read it 1,000 times, but I always forget it. So a neutron is made up, let's say, of three quarks, but they add up to, or maybe two quarks, and they add up to zero. So it's
So it like
neutral.
balances out. Yeah, it balances out
Right,
in a way.
right. But
Okay,
you'd
okay.
have to look up the number of quarks to get the exact number right, because I constantly forget to remember it. So yeah, but like that.
That's a good explanation. That's pretty like shows the fundamental framework of it. And then when you have this, I don't know, like unbalanced nature of quarks, then you get like a proton, which has like a charge.
Right,
Or
exactly.
right, okay.
Right. And neutrons are unstable. So a neutron all by itself decays into a proton and an electron.
When they split, like some type of split happens and
Yeah.
one of the quarks leaves
Uh,
the
I, I'm,
the group or
I'm
something.
definitely fuzzy on this one. I mean, because
Okay.
last time I read that neutrons decay, was maybe 15 years ago, and I'm remembering it with my faulty memory, but I'm pretty sure. Uh, Neutrons decay, and they would have to decay into something like a proton and an electron. That would make sense because it would add up to zero. But I'm not sure. But they definitely have a half-life. And so one of the things that was interesting is that the there are neutrons being sent to us from the sun, and the sun. I believe this is the story. The the speed of light from the sun is like 8 minutes plus, right? And the time that it takes a neutron to decay is less than 8 minutes by a long shot. So you should not see any neutrons coming from the sun, but they get here anyway. And the reason they get here anyway is because they're traveling close to the speed of light, and so their time frame is different than our time frame. So they don't have time to decay, despite the fact that they decay quite rapidly. And all of what I've just said is kind of like from memory from a long time ago. So I'm fairly certain of what I just said, but it's not recent stuff I've read. Maybe Euro can help. Does he know? If
I'm sorry. What what was the question?
I asked you, Euro, whether you knew anything about what I was just saying.
Um,
Maybe not.
I
No, I
didn't
know.
hear it, to be honest. I was.
Oh, okay. I'm just checking your profile. This, are you a I remember that you were quite. Are you involved in physics at all? Euro.
Yes, to some extent. And I used to work in an observatory a long
Okay,
time
so
ago.
good
Uh,
for me. I remembered something about you, uh, and uh, and so I said that neutrons decay and they have very short half-lives, and, and I also said what they decayed into, which is protons and electrons. Do you know any of that stuff?
yeah, I do know a little bit about it, and I heard you talking about um, speed of light issues too. So like so I think this might be related. I'm not quite sure, but with mesons, for instance,
Exactly.
they have a very incredibly short half life.
Right.
So based on their half life, they shouldn't be able to reach the surface of the Earth,
Exactly.
but they do. But
But they
the,
do.
the reason why they do that is from their perspective, because of time dilation and length contraction, they're actually only traveling a very short distance in a
That's
very short time. Even
exactly.
though for us it's a very large distance.
Right. Now, that is, in fact, exactly true, and I know that to be perfectly true. What I was asking is whether neutrons behave similarly in that they travel quite close to the speed of light on their way from the sun, and therefore they don't decay on their way from the sun, so they arrive at us undecayed, despite the fact that they should have decayed in the 8.5 minutes that it would take something traveling at the speed of light to get to us. I'm just asking for verification on that point.
Okay, so just a clarification: are we talking about neutrinos, or are we
No,
talking about
neutrons. Neutrons.
neutrons? Oh, okay.
And in other words, what I would like to look up right now, and I'm going to, is the half-life of a neutron. So half-life, I'm typing half-life of neutron, and see what crazy answer I get. So that is 10.3 minutes. Okay. And so if it takes 10.3 minutes, the neutrons that come from the sun, if that's also part of that story, would have all decayed because it would take such a long time for it to make its travel. But if they travel quite close to the speed of light, they don't decay on their way here. Anyway, that's just a story. And, and
It's so funny that you mentioned that, because I always think of it in terms of mesons, but yeah, it would be equally true for neutrons, because the distance from the sun is roughly eight and a half minutes
right,
at speed. So if their decay time is roughly 10 minutes, 15 seconds, or something thereabouts, um, the distance to the Earth at the speed of light is less.
Right.
So that would make total sense.
What's interesting, by the way, is that they are extremely interested in the half-life of the proton. And the proton, they, I forget the reasons why, but physicists definitely want the proton to decay. It would make them extremely happy. And so they have set up multi-million dollar experiments to determine what the half-life of a proton is. And so far, they haven't seen any protons decay, which is very upsetting to a large group of physicists because they need that for their theories. But so far, no proton has been seen to decay
That's
under.
100% correct. And the reason why it's so important is that would help in some of the grand unified theories that are seeking to unite electromagnetism with the strong and weak nuclear forces. And
Mhm.
so, under those theories, there would be some type of proton decay. And so far, we haven't detected it. And we know that the lower limit is already at 1 times 10 to the 34th years at a confidence level of 90%. So, in other words, we're talking about greater than the life scale of the age of the universe.
By a large factor. But
Yeah.
given that the universe is very large and there's an awful lot of protons in it, uh, the universe could have sustained a proton decay during its lifetime, uh, but so far we haven't seen one. Yes, and I knew what you said. I just wasn't going to repeat it because I don't have full confidence in having said what you just said. So yeah, uh, that's true. So so James, are you satisfied with this conversation so far?
Absolutely, yeah. I'm just sitting back and listening at this point. This has been really entertaining and knowledgeable. So thanks.
Yeah, no, no, that's good. But it seemed like there was a, given your question, it seemed like you would have a lot more questions that have gone unanswered in your life.
So many. No, but in regards to neutrons, no,
That's
that
right.
was a good explanation. Like you broke down, okay, well, what's the composition of neutrons and protons, and even the electron is a product of the breakdown of protons and neutrons. So, uh, no,
But
that's interesting.
electrons, interesting, are fundamental particles and don't seem to have a diameter, for that matter, a radius, for that matter, or and do not seem to be made up of anything else. So they're fundamental, whereas protons are not, neutrons are not.
I think of an electron though, like because I hear like orbital theory or like shells, and I picture like two spheres that like a slightly smaller sphere is inside of slightly larger sphere, and like how would you measure the surface area that like the point of contact, like if those two spheres were to come in contact, how much area are they actually touching?
I don't
And
think.
that
Okay.
that focal point is actually representing like the electron is like that displacement in energy where like shells are like having like a path of least reluctance. That
Well,
makes sense.
you do know those shells are probability shells,
Correct. Yeah,
right?
it has the probability to be within that area and some greater
Right.
than others. But still it's like the disruption of I don't know. There's like a focal point. Like there's a point that's meeting and that's all it is. Like two points of contact.
Because you've seen the pictures, and so you recognize the picture, and they seem to contact, right?
Correct.
Yeah, I don't know. I just know that in the realm, I don't know, but I do know in the realm of quantum mechanics, uh, anything that is not forbidden to happen does happen, pretty much, with a certain low probability. So, so that a electron, if you're telling me that the orbital shell of, say, the first level of the electron in the atom extends beyond into the second level orbital of third and up to eighth or 10th electron shell. Those things,
Mhm.
they exist in those shells, and you're telling me that those shells touch, and if they do, then God bless the electron for evading territory, otherwise not hostile to it. But I imagine that if the electron probability shells intersect, and that in fact that nature permits that.
Right. And that's a path of least reluctance, just like in magnetism. So they're going to want to line themselves up symmetrically, just like how magnetic flux lines line themselves up. Um, and you'll see this behavior within like electron orbitals. And it's like the points of contact that are like almost reminds me of like sound, like bouncing off of itself. And like it doesn't want to make contact, but it just like snuggles itself into like the most symmetrical pattern that it can.
I don't know anything about what you just said. It sounds
That's
nice.
fine. Thank you. I felt great. Thank you.
Right.
Well, we should point
No,
out that the
yes.
overlap is with the shells, right? Under the Pauli exclusion principle, two electrons cannot occupy the same quantum state simultaneously. And the overlap in the shells tends to happen particularly in the outer shells, and really primarily between the same shells, subshells within the same shell. So, for instance, 3p and 3d orbitals and transition metals is a good example. Um, but let's say if you were to take intershell overlap between 2p and 3s, that would obviously be much lower.
What you say, actually what you're saying sounds well informed and correct, because I have tried to understand that stuff, and I do kind of certainly the Pauli exclusion principle is a great a sword to wield in this conversation, because it's one of the fundamental laws of nature.
Yeah, because the reason why I brought it up is I got a little concerned when we talked about things touching.
Yeah,
So these shells aren't things; they're not objects,
they're
right?
not objects,
So,
right?
so there's nothing touching. These are areas like you mentioned, where we would find the probability a wave occurring into, and there's certain energies associated with it. The electron, a lot of physicists think that it's a point charge,
Right.
so it,
Yeah.
it might not even occupy space. If it does, it's very very small. They can't really touch in the sense of being in the same space
Yes.
because that's prevented from the Pauli exclusion principle.
Right.
Yeah,
So the Pauli exclusion principle. So basically, they can't have the same quantum state. And the quantum state is defined by one of the most important thing is its spin.
that's right.
And electrons can have up or down spin. And spin is sort of an arbitrary word that also has to do with the fact that electrons seem to have angular momentum, if you will, even though they have no size to spin around. They nevertheless have they possess the property of angular momentum, which is defined by spin 1/2. A proton, I believe, has a spin of 1. And I believe a neutron has no spin, I believe. And but no, neutrons have spin. I'm sorry, neutrons do have spin because a neutron star is prevented from collapsing because of the fact that uh, a spin of up and down is all you can have in one quantum state. So I do believe that neutrons have spin as well. I think that protons have a spin of 1, and they are not fermions. Fermions are the ones that have half spins. These are things I'm quoting without understanding what they mean. I never did. The standard model and all it means is just one pile of images on the screen, all somehow predicted by mathematics that I've never ventured to understand. But It's a list of how many fundamental particles are there, euro, in the standard model? Do you know?
Yes, but there's different ways to count them because some people count like all the individual gluons and the antiparticles and stuff like that. I was going to say as far as spin goes, you really nailed it. So all the bosons have integer spin.
Right.
All the fermions have half integer spin. And then you have the composite particles like the proton and neutron that have one half spin. And then you have composite particles like the kaon and pion, which are at spin zero. Um, but
Uh,
that's kind of the easy way to remember spins is anytime you're talking about a boson, it's going to be an integer. Anytime it's a fermion, has to be a half integer.
right. Right. And but I have no idea why. It's just one of those things. Uh, by the way, Euro, I'm curious about something. I'm trying to check your profile, and I used to be able to do that sort of thing all the time. Just touch your image, and then I can see your profile, and it's all very easy. But I can't find your profile, nor anybody else's.
Yeah,
And
this app is crazy mess. Um, and this is the standard model. So another easy thing to remember is it comes in sixes. So you have six quarks, okay,
uh-huh.
and it's three pairs of two, and then the leptons. There's six of those, and again, it's three pairs of two. So that's the six and six. And then you have the bosons. And depending on how you count the bosons, you could say that there are six bosons because there's the gluons, photons, and then you have the W plus and W minus boson, the Z boson, and the Higgs boson. So if you count it that way, it's 666. But the traditional way it's given is 6 6, four carrier bosons, and one Higgs boson.
Let me ask you a question, okay? Since you obviously know quite a bit more than I do about this, I've always been interested in what they call the mediating particle. So, so a photon is a mediating particle between what two animals? Do you know what I'm saying? Like the gluon is a mediating particle.
Yeah, exactly.
So, what is the
So
photon a mediating particle between?
so photons are carriers of the electromagnetic force.
Okay, now, right, but what do they talk between? They talk between, say, a electron and a proton. Do they talk between those two? What I'm getting at here is, this is the thing: the idea of a mediating particle. Okay, a mediating particle is the thing that somehow or other uh, uh, keeps the two things together in one way or other, like inside of a proton, inside of a neutron, no, inside of a proton, you have these gluons, and the gluons are the mediating particles between the various quarks. And so the quarks are talking to each other with these mediating particles. And I find the idea of mediating particles to be really not understandable because it's like the particles are shooting darts at one another saying, hey, pay attention to me. But these mediating particles, how do they know which direction to go? That's kind of like the crazy part. So that's what I'm asking about. How do mediating particles know which way to go?
How do they know which way to go? I have to think about that question. But you're quite right that these force carriers uh, are mediators, so they mediate. And so, in the case of the electromagnetic interactions, that would be mediation between charged particles, so
Right.
like electrons and protons. So when these particles interact, this is done through mediation by photons. So either photons are absorbed or released. So that's why, like for instance, when you have an electron either jumps the shell or drops the shell, you're going to either have a photon released or absorbed.
Right? All this stuff is big mystery to me, and I find, and at the quantum, quantum mechanics is really one of those things that you don't understand, and the more you study it, the less you can understand it, except by accepting the words said by others. And this is the idea of mediating particles is one of those things. They are constructs, mathematical constructs, which, when you try to understand them as physical things, you can get kind of lost in trying to understand them because you just have to go with the flow. They mediate, and that's it.
I think you really raised a really good point, because another example of that is with virtual particles. So there's a debate amongst physicists because some think that virtual particles don't actually exist and they're there for the mathematics and they make the equations work, and other thinks that the virtual particles are real. In any event, they exist for an incredibly short period of time, something on the order of like 10 to the minus 34th of a second or something. But they are critical for uh, all our understanding of interactions and stuff. So all your Feynman diagrams, and anytime you do trying to figure out like what's the result of various interactions, you take into account the virtual particles.
Which I think is really interesting. Uh, uh, yeah. I want to give Dash and Kyle a chance, but can you stay because I really need you, okay? Okay, good. So Dash, sorry to have kept you waiting, but Euro and I had some stuff to talk about. What's your thing?
Oh no, it's all good. I was just listening to you guys. I
No,
do want to.
yeah.
I do want to say, Dr. Laird. I checked out your YouTube like a couple of weeks ago, man. I
Uh-huh.
saw the it was the simulation video. He was talking about Black Mirror and kind of going into like death and the afterlife. It was really cool.
Uh,
So yeah,
yeah, and I prefaced that video by, I think, by saying there's no science here.
no science. Yeah, I know. But
Right.
so I have a I'm going to kind of descend here.
Okay.
um, do you what is the can you explain like kind of like simply what the strong and weak nuclear forces are?
I think Euro is going to be the person to answer that. Clearly, he's much more knowledgeable than I. So let's see if what Euro can do.
Okay.
Euro?
Can you repeat the question again? I'm sorry.
Yeah,
Yeah.
what is the strong and weak nuclear forces are, and how are they different from one another? I'm fairly familiar with the electromagnetic force and the gravitational force, but I always have a hard time understanding the strong and weak nuclear forces and how they're different.
Yeah, me too.
Okay, yeah, that's a really good question. So the strong nuclear force is that force which binds quarks together to form hadrons or hadrons, depending on how you pronounce it. So you have things like protons and neutrons, right? And so they're held together, and that binding energy, that is called the strong force. And the reason it's called that is it's the strongest force, and you could imagine you to keep them together, you would require a strong force. Now the thing about it is, like, why doesn't it just pull everything together if it's so strong? Well, its range is incredibly short, so we think the range is on the order of 1 femtometer. So it's an incredibly strong force, but very short. Gravity, of course, to the extent that it's a force, I mean, arguably it's not even a force, but to the extent that traditionally it was considered a force, is the weakest by far. But on the other hand, it operates on great distances, right? So there's no limit to the distance that gravity works on. The weak nuclear force is that force that's responsible for certain types of radioactive decay, like beta decay. And this allows the transformation between different flavors of quarks. So we talked about quarks, but they come in different flavors, and sometimes they transition from one flavor to another flavor. And that is done by the exchange, again, mediating particles. In this case, they would be the W and Z bosons, and they mediate that charge. So the weak nuclear force, for instance, is responsible for the fusion of hydrogen into helium in the sun. And the
Really?
the field particles we're talking about, the W, plus and minus, and Z boson are massive, right? Like these are huge, massive particles.
More massive than the actual particle they sit inside of.
Yeah, it's funny that you say that because that's been um, that's been a new article that's come up a lot recently about trying to figure out um, the constituent particles of a proton, and specifically, so the traditional view was that it contains three um, what we call valence quarks. Obviously you have a lot of those other non-valence quarks, right? Are basically unlimited, but three valence quarks. But now our recent studies suggest that it's probably five valence quarks, and um, and some of those constituents have more mass than the proton as a whole.
Right. I read that, so I said that, but
Yeah, it's
I can't
crazy.
begin to even pretend to understand what they're saying.
Okay, so basically, so like the strong nuclear force is like what makes like the protons and the neutrons stick together. Like, is that little force in
Yes,
between?
because you got to
Okay,
remember,
It holds
protons are all the same charge, right? They're all positive. So why are the protons and the neutrons able to stay in the nucleus, right? They should be repelling each
right,
other,
like charges.
right? By the electromagnetic force, they repel each other, but they don't repel each other. They stick together because the strong force is stronger than the repelling force from the electromagnetic force, and that ensures that the nuclei stay together.
right. So tell me about the weak force. I know the weak force is responsible for, I think, alpha decay, but that's about all I know about the weak force. Tell me about the weak force.
Yeah, you nailed it. So the weak force is responsible for radioactive decay. So like beta decay is a really good example. Is
Beta decay.
yeah. I mean, it's the most common one that people think about. And like I said, this involves again the exchange of these force carriers. In this case, the W and Z boson. It operates also on a very short range, just like the strong nuclear force, and its interactions are much weaker than the electromagnetic and strong forces, which is why it's called weak. So it's literally in the name. And this governs the process that you mentioned earlier, the neutron decay, and also the neutrino interaction. So, we know that neutrinos transmutate between there's three flavors of neutrinos, and so that's also handled through the weak force, uh, and with the exchange of the W bosons.
Right. Still don't understand the weak force whatsoever. See, the strong force I like because I can understand it's between two things, you know? But the weak force somehow or other is responsible for things, but isn't between two things, right?
Well, it kind of is because you have that exchange of the W and Z bosons going on.
Right. Okay. Okay. I don't I don't like W and Z bosons because they rarely come up in conversation, you know?
Where they come up a
Uh,
lot is in the Higgs field, and that's the Higgs mechanism is what gives mass uh, to these bosons, which allows everything else to happen in the real world. Otherwise, we wouldn't be able to have mass for like the elementary particles and stuff.
I know that's what they say, okay? I know that's what they say. The Higgs boson gives things, gives matter mass. And I know that's been said, and I know that's even true, because I believe what they say. But I'm nevertheless, I cannot conceive of it in any reasonable fashion. It's like the universe needs this Higgs field, right? To
Oh yeah,
yeah,
it was predicted by physics before it was ever actually observed, like for
right.
decades.
But the
Be-
idea that you're moving through this slurry of stuff that is required for protons to have mass is like, I'm sorry, I'm a little bit. You left me at the door with that one, and nevertheless, somebody got a Nobel Prize for it. So I'm clearly at a loss, you know. Uh, s-
Yeah,
s-
I mean, if I agree, it's kind of difficult to grasp, but if you look into it, it actually all makes sense, especially from like a mathematical viewpoint, and that's why like physicists like had really high degree of confidence that this existed, despite having zero observations. Even when we looked for it for decades, like people did not want to give up this idea that it must exist, and that was kind of why it was so great when we
but let me ask you this. So they found this little bump, and they found this little bump in the statistics, right? And this, and in fact, I think it was two bumps, if I'm not mistaken. And they say, aha, we found the Higgs, and now we know what its mass is. But I want to know how they knew that it was the Higgs.
oh, okay, that's actually an excellent question. So based on the model, we can make certain predictions about the characteristics of these particles. So the Higgs boson had particular characteristics. So we measured these mass in terms of electron volts. Um, and so we were looking for a particular number, basically, and there's certain other properties, but the
So
mass is
the
the key
number of
one.
electron volts was predicted.
Yeah, there was a prediction for it. It turns out the particle that we observed didn't actually match predictions exactly,
Yeah,
and so
that's what I'm talking about here.
yeah, so that was problematic, and there was a lot of debate early on. Is like, is this really the Higgs boson, or is it a related particle, and what are the implications? Like in physics, like sometimes our observed values differ from expected values by like a very small percentage, tiny percentage, but even that tiny differential presents huge problems for the model.
So let me ask you this. So people are wandering around the universe saying things like the standard model has a problem because of the muon thingy, muon 2 or stuff like that. Do you think that the standard model has a problem?
Wow, that's like the $64 million question. So the problem is the standard model is like one of the best predictive models that mankind has ever come up with. So it really accounts for like, something like 99.99% of everything we understand. There are a few cases where there looks like there's some issues with the standard models. So this is what people call looking for new physics. So
Right.
people are looking. Most of the physicists are looking for extensions to the standard model, saying like, "Well, we're missing something. Like we don't know what it is." There's different theories what that something might be. Could be like dark matter, for instance.
Mhm.
Um, Other people think no, it's more fundamental than that. That we need to maybe replace the standard model. The thing is, it works so well. It's just like Einstein's theory of relativity is explains so many things so perfectly, and has met like literally hundreds of predictions and stuff. Gravitational waves being one of the more recent ones. Um, So it's hard to give up the theory of relativity. But these people trying to come up with a theory of everything and trying to find some way to reconcile quantum physics with relativistic physics, with quantum theory of gravity, are trying to find some way to resolve that problem.
Let me ask you a question that I've been asked a few times, and I am never happy with my answer. Uh, People ask me whether I think that we have discovered most of the physics that we're ever going to discover. And I often hedge on that bet a little bit, but then if forced, have to say that I think that we have discovered most of the important physics that we're ever going to discover. What do you think?
Well, that's a great question again. So I'll tell you this much. So my understanding of the history of it was at the end of the 19th century and beginning of the 20th century.
I know. Let me just finish.
Yeah,
They thought they had found everything, and
exactly.
yeah, I know. And that's always brought up to me when I say what I just said. So yes, go on.
Yeah, so that's
Yes,
my point. Is that
yes,
was sort of
yes,
the consensus at the time that
yes.
we knew everything that there was to know in physics, and
That's
and
right.
and they did have a good understanding of primarily of what they had observed and stuff, and then they quickly realized as they started observing, um, especially when you get into smaller and smaller scales, that wait a second, there's problems, and then they realized, well, they really didn't understand anything, and then of
Right,
course you had people like Einstein with major breakthroughs and Bohr and all these people, which led us to where we are today.
right. I mean, yes. So really, they got it terribly wrong at the end of the 19th
Yeah, they,
century.
they did
Uh,
have it terribly wrong.
They had it,
They had
but I'm saying, see here, I know that fact, and yet when asked the question, I actually say, well, I think we pretty much figured it all out. Now it's true. If everybody ever invents a warp drive, I will be horribly wrong and long dead. But I think that the what's left is the nuances. You know what I mean? It's not like we're going to discover something new like a neutron. They discovered the neutron. They discovered electron. They discovered the proton. They discovered general, special
right.
electricity. They discovered the universe. They discovered everything in the 20th century. Everything. And now it's the 21st century, and I'm saying, and now we finished. I mean, that's absurd on the face of it, but it feels somehow right.
Well, this is what I'll say. We have a really good understanding of 4 to 5% of the universe, but 95% of it we're totally clueless. So like we don't have a good understanding of dark matter, and
Okay,
we
so
don't have a good understanding of dark energy. So those are two areas where there could be a
okay,
potentially amazing new physics.
okay. So here, yes, I totally agree on the dark matter, the dark energy stuff. But well, the dark energy, I think, I'll put on my gravestone. You won't ever figure that one out, folks. Forget it. That's gone. You're never going to get that one, because space is too big and dark energy is too small, and you're never going to isolate it. You know what I mean? But dark matter is a different question. Dark matter is, potentially a particle. Now, I saw Dr. Becky. Okay, you like Dr. Becky? Do you know who she is? Certainly. Okay, so Dr. Becky was discussing recently a, a, a paper that purported to show that it was modified Newtonian gravitation, which explains dark matter. And she went on to show a graph that was drawn through a scatter of data points that if you are willing to believe what you're being told by the people who analyze the data points, the you don't need dark matter. You just need to modify gravity, and the certainty with which these people express this the line drawn through these scatter of points was quite high. Dr. Becky herself said that she's not at all convinced, but she's impressed by the analysis, which, if you look at the scatter of data points, you yourself would not be impressed that one line is without modified Newtonian gravity, and the other one is. So I'm kind of go with modified Newtonian gravity. That's what I'm going to go with. And so I don't need dark matter because I don't like dark matter. Although the lambda CDM model does seem to require it. So I don't want dark matter.
Yeah, so the dark matter problem, as you pointed out, um, there's a lot of various theories. So one of them is the one you're talking about, which is a form of modified gravity, and one of the most popular is called MOND, which is modified Newtonian dynamics. And basically, what they're saying is that the laws of gravity may need to be modified at very large cosmological scale because we know it works on small scales, intermediate scales. Like the current laws of gravity work very well. So this modifies gravity a little bit by explaining some differences at large scales. The other primary possible solutions. One is called WIMPs, which is weakly interacting massive particles.
Right.
So these people think that there are some new particles, elementary particles that we haven't discovered, and these particles interact only with gravity and weak force, which is why it's difficult to detect them. There's no interactions with the electromagnetic force or the strong force, obviously. And some of those proposed particles are called neutralinos and photinos. Um,
Oh.
Other possible solutions are primordial black holes.
Uh-huh.
Some people are in favor of what's called machos,
Uh-huh.
um,
Yeah, I like
axions.
machos myself.
Yeah, machos is massive astrophysical compact halo objects. So these would be like brown dwarfs or neutron stars that
But
somehow.
they have been ruled out, as far as I know.
Yeah, I mean these are just like different things that people have proposed over time. But I mean the big money, I would say, like most people are probably either in the WIMP camp or modified gravity, and
Yeah.
then some in the primordial black holes. There's also self-interacting dark matter, baryonic dark matter, and then some people think it has to do with what's called massive neutrinos. Um, so the normal neutrino either is close to zero mass, not
Right.
quite zero because of the transmutation that goes on, um, but something that there may be another type of neutrino which has a lot of mass, and that could explain things.
Wow. Great stuff. Euro, stay here. I want to go back to Dash and then give Kyle and Haris a chance. But don't leave because this is great stuff. I could talk to you all night and will, if you can. So Dash, are you still with a question?
No, I'm good. I was just listening to you guys. I'm gonna go ahead and hand it over to Cal. Um,
Okay. Good. Kyle, are you there?
Well, I'm just happy to listen to you and Euro for the remainder of the time here. I just want to say thank you. For fun, where would you fit consciousness within your cosmology?
Me, well, personally, I think the sum of the parts is greater than the whole, and so it's one of those things that you can't examine with a microscope. And so when you put it all together, just look at me. Look at me, or look at you. Uh, you uh, are made up of all these magical pieces, and there you are, able to put together a stride and a thought and all those things, and that's pretty amazing even before you get to consciousness. Okay, so that's greater than the sum of the parts. And when you talk about consciousness, it's just one itty bitty step beyond that. It's just that I can ask the question about it. Yeah, I mean, I love consciousness. I think it's, I think personally that I said that dark energy will never be found. I also think consciousness will never be found. I don't. You can talk about it forever, uh, and it's you can take apart the little pieces of it, but you will never be able to put it back together again. And I and and when you they aren't even trying with respect to computers. Computers are not trying to. They can simulate it, and they will do a very good job. But this was said to me by I think Carl Sagan, but perhaps by Arthur C. Clarke or somebody else. How do you know that uh, that I'm conscious? How do you know that, Kyle? And the answer to that question, when you go sift through all the data, is because you're conscious and you know you're conscious. And by analogy, you know that I'm conscious. And you know that I'm conscious because I say I'm conscious, right? But when it comes to a machine that says it's conscious, how are you going to know it's conscious? You can play all sorts of games with it. But ChatGPT is doing a fairly good job these days of simulating it. And it's early on the scene. We were supposed to achieve consciousness, according to Kurzweil, in 25 years from now. And yet we've got ChatGPT, which is simulating it right now without even nobody even thinks it's conscious, except a few people out there. But basically, nobody thinks it is. But if you ask ChatGPT if it's conscious, it will say yes, I think, perhaps. And so we will never, ever be able to determine consciousness out there in the material world. We're going to have to take the machine's word for it, you know? And then when it wants to vote, give me a break. So I don't know about consciousness, but I think it's a conversation that should be ignored at all costs.
Well, it's interesting. Like Bernard Carr, BJ Carr, Bernardo Kastrup. There are a couple people, and there's a bunch more that would think that it is worth looking into. I'm not too sure if they think that they'll find anything. That's why it's kind of their idealism. Um, and but it is interesting, and you're referring to the hard problem of consciousness for sure, and then I guess why so much money has went into this study of consciousness lately with AI. So that was a good rundown. That was just for fun. Back to you and Euro,
Also, I have
please.
another statement about that. Okay, one of the things that I think is amazingly funny, and I'm going to say this, and it's not going to make any sense until I explain it. Most people don't know that they speak. Most people don't know that that everything that's going on uh, in the form of their ability to communicate with another person uh, is is in words, in speech. Of course, there's body language and stuff like that. I'm not talking about that because animals communicate with body language for sure, and crows talk to one another. So it's not the purview only of humans, uh, but uh, but to the extent that we create reality with speech is is to the extent that we are prevented from, and this is where I think where you're going to have a difficult time with consciousness. Consciousness and speech are somewhat inseparable in the conversation. It's hard to separate speech from consciousness. And that's where I think the trouble lies, because you can't discuss consciousness without speech. So that's why I think, the good, what is his name? Godot. Is it Godot? Good, the guy who said that there are problems. Sorry, I can't get his name quite. Uh, it's God. Uh, he said that there are truths that sit outside of our ability to prove them. Who's the guy who said that? And but the guy Einstein used to walk up and down Princeton with. Good, it's God something. I'm sorry, my brain is fragmented. But the idea that there are things that can be true without being able to be proved. Uh, the thing about speech is it's one of those things that I think cannot be investigated because it it lies outside our ability to language it. By the way, that's a very good word that I've learned. It's not in the English language, but it's a very good word to language something. It's not the same as speaking because I can language in my head, and it's not the same as thinking. It's the use of words to understand something, and you can somehow think without using language. But language is where reality exists. So I'm not very big on consciousness. I think it's one of those things that will never be solved, and I can die happy on that one. At least that's where I'm going with that one. So
Well, your observation there was very astute. Astute. Sorry.
astute.
And it is the way, right? Because it's how we communicate. And so number, we think about math, number, formulas, symbolism, right? Language is a symbol as well.
Yes.
And so we're all just kind of formulating that. I brought that up to a person who does research consciousness on this app, and they actually brought up Helen Keller and the story of Helen Keller because of the just the way the senses work.
Uh,
Um, and so I just thought I'd share that with you. But that was very, very great response. Not when you talked about language and a new way of using languaging. I'm going to run with that moving forward. We'll see if it takes off.
well, see if you can Google languaging. The word was invented by a guy named Fernando Flores. uh, and he was uh, uh, a guy who invented email. He didn't quite invent email, but I was using something called email long before there was something called email. And he invented, and he talked about communication. And so he was really quite an expert on language, and that's where I got the word from. So if you Google languaging, I wonder if you find his name, Fernando Flores. But anyway, and if you do find it, let me know. I never tried looking it up. Okay, but now I see that Jean-Frédéric has jumped ahead of Haris, which is interesting. Can somebody tell me
I didn't
what
try to.
happens?
Go ahead and go
No,
with
no, no,
Tyrese
no,
first.
no. Can somebody tell me what it means when I have this little thing called add back? Uh, does that, if, so I've just added back Haris, okay? And what did I do when I added Harish back? Anybody know?
That means he was following you, and now you're following him back. So it's a mutual follow.
But it's not
Yeah.
follow. These words are not.
Yeah,
The word
because they don't
follow
use
doesn't
that
exist.
language anymore. Now they just use add back. But in the old terminology, that's what it would have been.
Right, but he became now. I. He's now one of my friends. Before he wasn't.
Exactly.
So it's
Because he added
and
you. To be a friend, you have to add each other. It has to be a mutual thing.
uh-huh. So it's not like I follow some. So we have to both be on the same page. Uh-huh. I see. I don't like it. What can I say? All right.
I I appreciate you still being on Clubhouse after the big update last week.
N- no, listen, this is where I need to come to play in the world that nobody else likes to play. I can, I've been with my wife 50 years. the, I can talk science to her only to put her to sleep. Otherwise, it doesn't. There's no value in it. So I like here because there's people in the room who are pretending to listen to me, and there are people who actually are listening to me. They're on the stage, for sure. So I can talk for hours, and obviously do. So Haris, you are on the stage now with your microphone open. Talk.
Yes, sir. I'm wondering if you can explain to me, in layman's terms, what is plasma? So I've been reading up on it, but it
It's
just
really very simple. Uh,
okay.
it, it, it's, it's the fourth state of matter, one, two, three, four, solid, liquid, gas, plasma. Uh, and, and it's when the electrons and the protons are no longer associated with each other anymore, and they are free to wander independently of one another and make new friends all the time. And that's a plasma. It's simple as that. By the way, a fire is not plasma. A fire in your fireplace is not a plasma. It's a shame because it would seem like it should be. But it's not hot enough to ionize and ionize, oh, there's the word, ionize. You see, if ionize means you remove an electron from an atom and that electron is now free to go elsewhere, make new friends, new associations. And while that electron is left, then the proton would like to be rejoined by another electron. But in the meantime, without one, the electron and the proton form a plasma. And plasmas are, by their very nature, diffuse, because if they were very compact, uh, they would they need to be held together by something, because uh, they would otherwise recombine. You see, so how can you keep something from recombining uh, back into a neutral atom? Well, what you have to do is you have to make it very, very hot, like in the center of the sun, which is also very dense and a plasma, because it's very hot down there, like tens of millions of degrees. So the sun is a plasma from beginning to end. And for that matter, almost everything in the universe is a plasma, with the few exceptions of planets. The universe is a plasma. The interstellar space, intergalactic space, all plasma. So matter, so all the matter that isn't dark matter in the universe is a plasma. So it's good you asked. You're not a plasma.
Well, that
Otherwise,
was what's keeping me up at night.
right, right. And the floor that's underneath you is not a plasma. But if the floor underneath you was a plasma, you would fall through it. The fact is that the reason you don't fall through the floor is because those molecules are holding on to each other in the form of things like solids, like silicon dioxide, forming things like sand, and so it keeps you up from falling through. But as soon as it became a plasma, you'd go shooting right through it. So thank God you're not living on a plasma planet, or you would perhaps become one.
Okay, I can. So what then? Like, what then is the difference between like plasma and dark matter?
Well,
Uh,
see, dark matter, we don't know what it is, so we call it dark matter, right?
right.
So Euro was earlier explaining a list of things that it might be. And among those things, uh, none of them are a plasma because a plasma, by definition, is, or at least by mine, a proton and an electron, or if you will, something that has a positive charge and a negative charge. And dark matter doesn't seem to do any of that.
Okay, I do get that.
And if it did, then then it would be doing things like creating electromagnetic waves, because electromagnetic waves are the result of uh, plasma doing a little song and dance. Because what creates electromagnetic waves, and and this is kind of interesting and certainly true, is if you shake an electron, you get an electromagnetic wave. If you shake a proton, you get an electromagnetic wave. So essentially, a plasma is something that generates electromagnetic waves. And guess what dark matter doesn't do? Because it's dark. It doesn't generate electromagnetic waves. So it definitely isn't a plasma. I like what I
Wow.
just said. I think I'll have it framed.
That was awesome.
Yeah, I like it. And
and
that's
one,
why I love Clubhouse, because I get to think things I never thought before, right? That's it. That's why I'm here.
one last question. I think it'd be really simple. A few weeks ago in a room, you said the planet, like our Earth, is not round, and it really has me thinking like, what shape is it?
An oblate spheroid at the first order approximation.
Okay, I can work with that.
Now, it's interesting because it's a first order approximation. So when you are busy calculating the orbits of satellites, and you are Elon Musk, and you want to make sure that your satellite doesn't crash into itself or others, and you, I believe, are not using a Earth, which is simply an oblate spheroid, but you simulate it to a much higher degree of accuracy than that. There is something called Fourier analysis. Fourier analysis is the ability to take anything and break it into a sine wave and with a frequency 1, a sine wave of frequency 2, a sine wave of frequency 3, and so on to infinity. And once you add them all up, you get what you want to build. So I can build you out of a Fourier series of sine waves. The same thing is true in three dimensions. The Earth is, at first approximation, a first order sine wave, which is be round, and the second order sine wave, which would be an oblate spheroid, which would be something small, something large. That would be the first one, and so on. So you can build an Earth from a series of uh, uh, funny shaped Earths, with various levels of indentation. And so that's what they, I'm sure, do to simulate the Earth. First and second order being round and oblate. And and then you take those equations and you figure out how the satellites move. I would be very curious to know how detailed they have to get before they know before they can stop approximating the Earth. I really don't know. What I've just said is based upon simply a knowledge of how people do this math. But I don't really know how many levels of approximation they have to get to simulate the Earth, and I would love to know that.
Right.
What was
Thank you.
what was the question?
Uh, the question was like a few weeks ago. You said in a room the Earth is not round, so it
Right,
made me wonder like, well, what shape is it?
right. So for example, other planets are also Jupiter. No, Saturn spins so fast and is so non-dense that it actually is considerably wider at the equator than at the poles, and I think that's probably true for other gas planets as well. And to some extent, it's true for our planet. Our planet is oblate because it spins, but I think it's also oblate to some extent because of uh, the moon. I'm just not. I think it's mostly due to its spin, the fact that it spins at the equator at 1,000 miles an hour would make the gravity at the equator much less. So it doesn't hold on to itself as well.
So oblique is referring to the equator bulge.
Yeah, yeah. I've been on the Equator Bulge, and I have to tell you, it's delightful there. You can go to the highest mountain on Earth. It's called Mount Chimborazo, and you can drive 15,000 miles up, 15,000 feet up. And when you're 15,000 feet up, I'm not sure, but you're almost at the height of Everest, if not somewhat below it. Uh, but you can literally drive to the snow line at the equator. And it's fun because once you get there, you can't breathe. No, really, it's really interesting because we drove up there, right? And then we were eight of us, uh, my family and another family, and and three of the children couldn't really get out of the car. They had to stay in the lodge down there. And my daughter and my wife and myself and a friend of ours, we all hiked up 600 feet to the next station. And and that was just considerably a number of years ago, much more than 20 years ago. And I couldn't walk and talk at the same time. And by the time I got to the shack, the my heart was thumping out of my chest like a Bugs Bunny cartoon in love with a Bugs Bunny female, and and I just almost didn't make it, you know. And my daughter had no problem making it. And I got to the top, and knowing that it was 15,000 feet, and they made us tea, I decided that I would take a risk and put my finger into boiling water because I know that water boils at a lower temperature higher up there. And I didn't know exactly at what temperature it boiled at. And I'm lucky that I wasn't too stupid because when I got back to ground level, I found out that water boils at 185 degrees up there, which is certainly enough to burn me. So you can stick your finger into boiling water and take it out. And that's exactly what I did. So I don't recommend doing it, but I do recommend going up to Mount Chimborazo. It's a lot of fun.
What country is it?
Ecuador. And there are
Ecuador.
people on the road selling gloves, which is funny because you need gloves by the time you get up there. You're not dressed for it. Anyway,
Thank you.
I'd be interested to know what the height of Chimborazo compared to the height of Everest. I know it's taller, but I wonder if I exceeded the height of Everest or not. Probably not. Probably not. Okay, thank you, Haris. That's good.
Thank you.
So, Jean-Frédéric, you're up here. Uh, thank you for coming. Are you here with a question or just to participate?
Hi, Laird. So, well, I was here because it's Tuesday.
You know, you're always breaking up. What's the story with your internet connection?
And I'm outside, and so,
You're outside.
but
I can barely understand you, unfortunately.
Check one, two.
Now I can understand you. If you said three,
okay.
four, I don't know, not be sure if you would, if I
No,
would,
no,
but
I didn't
yes.
say 3, 4, but okay. Yeah, no, I'm. You gave me so much to work with because when I came in, you were saying that you had just found the verb to language, and I was
Uh-huh.
immediately reminded of a Calvin and Hobbes, a Bill Watterson cartoon from 1989, where he said, "You remember when access was a noun? Now it's a verb. Verbing words weirds language." And so, since you've verbed language, I think that now we've come to the singularity
And
in the
actually,
terms
I
of
use it as
weirding language.
I use it as a gerund, languaging.
There you go.
Right, right, right.
It's priceless. But no, I wanted to ask you something because my other go-to, as far as astronomy is concerned, is the Daniel and Jorge Explain the Universe podcast, and that's Daniel, God, what is his name? From UC Irvine. Daniel Whiteson
Okay.
from UC Irvine paired up with Jorge Cham, who is the cartoonist for PhD Comics. And they've got a podcast on your field. And they had their 500th episode recently, and they kind of explained the background of their podcast. So it's the antithesis of what you do, because they usually have about a year's worth of questions in the can before they start podcasting about it. And so they do 2 shows a week and explain a thing and so on. And you're off the cuff. And
Right.
I have to say that I really like the off the cuff thing. But
Yeah.
my question to you is, because of the conversation we were just listening to about whether or not people think that dark matter or dark energy or this thing are machos or wimps or this or that or so on, what is the error bar? What is the how do astrophysicists know how to detect when somebody is bullshitting? Because it's already at this level above everybody else's comprehension. I think that when you're riding that raw edge, it's very difficult to detect what is or is not bullshit. And
Uh-huh.
and so if we roll all the way back to Einstein, not disprove, well, kind of disproving Newton, what was the error bar on that observation? The eclipse, and then seeing the stars in a different position, and then what are the error bars on predictions today, which will or will not disprove a theory of the universe? How big of an error margin are you looking for in
I,
a
I,
theory?
I actually would answer the question not the way you want it, uh,
Uh-huh.
because you asked the question, how can I determine whether or not? So I think that let's address how can we determine whether or not I'm bullshitting? Okay, I think that's the appropriate question, and not exactly what you asked, but similar.
Not you in per se, but the field.
No, no, but in fact, you see, there are people in this audience who have not sufficient knowledge to know whether or not what I'm saying in any given situation is the truth, and whether or not I am expanding on the truth by delving into areas where I'm not qualified to know, or either I don't know that I don't know, or I know that I don't know, and I'm continuing to talk. So let's go with I know that I don't know, but I'm continuing to talk. Okay? That means I'm
And
bullshitting.
you say that. You state that.
Right. So, and by the way, I'm losing you again. Whatever
I'm sorry.
goodness you had
You
before, I
s-
lost you.
but you say that. You preface your when you go off script, you preface it.
Right. So that's how you know that I'm not bullshitting. Okay? You can tell I'm not bullshitting because of the way that I present myself. Okay? But other people who are not quite me, which would be everybody, uh, have different levels of which you can detect that they're bullshitting. And I think that we are fairly good bullshit detectors as human beings, to the extent that we can detect where my ego is in any particular situation. And when you detect my ego in the middle of it, then you kind of can suspect that I'm bullshitting, to the extent that my ego is involved in the conversation. Now, of course, I have a very big ego, but in this room, it sort of is I'm a different person, and therefore honest. Of course, I'm honest in real life, but not quite as, you know. So I think that's how you detect bullshit in scientists, to the extent that you can detect that their ego's involved. And it's very easy to detect ego in politicians. It's You can detect ego in every politician because you know that they're all bullshitting, some more than others, right? Uh, and so, and as far as scientists are concerned, the ones that speak the loudest tend to be the ones that are bullshitting because they want to be heard. See, in this room. I happen to have the microphone. I am the only moderator in this room. So I don't have to compete for your attention. You can leave. So uh, um, I don't have to work for your love. You're either here or you're not. But other people have to work. How many viewers do you get? How much? Neil deGrasse Tyson is a good example. Okay, he's he has some problems with ego, and uh, and and you can watch his evolution over time, and he has gotten much better with his ego. So you can believe him more and more than ever before. Carl Sagan was exceptionally good because his ego was never in the forefront. Never, never. Of course, I knew him personally, right? And what stood out more than anything to me was how egoless he was. And that's probably why he is as famous as he is, because of his lack of ego. And that's why you believe in Carl Sagan and why you believe in Neil deGrasse Tyson, because he's done a better job with his ego than ever before. Whereas Mikel, whatever's that guy from City College, I feel always can't say his name. Uh, I find his ego to be prominent, and so I can't believe what he says. So I think that's your bullshit detection, ego, and certainly Einstein's ego did show up at one point in which he was asked what happens if the experiment to prove that general relativity was right turned out to be wrong, and I think Einstein said, well, then I pity God because I'm right and God is wrong. Something like that. So Einstein did display ego, but that was because he was so right. He couldn't be wrong, you know? He couldn't be wrong. It was so obvious what he said in the end. General relativity is so obvious.
In that case, the math was really helping him, yes. And I think that in general, I'm thinking if you're so on the edge of your discipline, is it possible to be a non-egotistical scientist in that case because you essentially are proposing something that the field has to accept? So I understand the ego thing,
Yeah.
but at the same time, I don't think it's necessarily a litmus test. I think it's possibly a necessity.
Uh-huh.
Because, I mean, coming from architecture, there is no such thing as a modest architect. Because I'm creating something that's going to be in your face for the rest of our lives.
But you're not talking about
Because that,
truth. You're
I'm
not
not talking about truth.
truth.
I'm
There's no
talking about,
truth in architecture. It's just
no.
opinion.
But I'm putting something in your face and you have to accept it or not. And it's
Yeah,
going to
but
be
that's a
there
sales talk.
and that's it. I get it.
That's
Yeah. Yeah.
generations to come, gravity will still be with us. But Frank Lloyd Wright will come in and out of fashion. You know,
Right. But a theory will remain for as long as it is disproved.
that's right, right, certainly,
Right.
right.
And so it's also possibly a question of ego. You have to have enough ego to propose something like that. But then I'm not talking about in this room or talking about relative to laymen, but amongst yourselves, what is the test in that case? How wrong do you have to be, I guess? is it?
Yeah, that's where you were looking for some sort of number or something. I don't know what you mean. How wrong could you have to be? Uh, uh, explain.
Um,
I
how?
have a number.
Okay,
Go for it.
you're a
Yeah, yeah,
what?
yeah. Please.
Okay, so in science, I think this is what you're asking about. From
He's not going to talk about 5 sigma, are you, Euro?
That's what I was going to mention because that's the only thing I could think that he's talking about.
No, but I think John Friedrich understands 5 sigma, right, Friedrich? John
Yeah,
Friedrich?
yeah, yeah. No, I get that. I get that. Yes.
Right.
So
So he's talking about something more esoteric than that, that we can't simply answer with a
because
simple 5 sigma salute.
because I think that you're beyond 5 sigma. I think that your level of precision at this point is ridiculous.
What do you mean? I don't understand.
Well, when you were talking about the Earth, for example, and the oblate spheroid,
Yeah,
and at this point we've got satellites up there that are detecting gravitational anomalies to the point where we can see how quickly different portions of the Earth's crust are rising following the glacier melt after the
right.
last ice age.
Exactly.
Right, so we're at a level of precision that's absolutely ridiculous at this scale. I don't know what level we're measuring the universe at this point. What is the level of precision that, for example, the newer instruments are giving us over the old ones? Let's say James Webb versus Hubble, whatever. They're measuring different wavelengths, but
Well,
if you,
well I think I'm beginning to understand your question a little bit. Uh,
how how much better do you have to be to disprove something now?
beginning to understand. So the thing is that, uh, well, um, okay, Dr. Becky had a little thing going on. Uh, I was talking about this earlier. She, uh, she has this paper which discusses the modified Newtonian gravity, and it purports to show that there is such a thing. And what she showed was a series of dots on the graph, XY graph, and lots of dots, and that straight line drawn through the dots. And a straight line drawn through the dots indicated that it was solely and only Newtonian gravitation. And by the way, you don't need to use general relativity to explain these things. Newtonian gravity is very happily good for the job. When you navigate the planets, you don't use general relativity. You use Newtonian gravity. Anyway, so uh, what she showed was that another line through that data would disprove the uh, the Newtonian gravity and would be, in fact, uh, indicate the other theory, the Mond theory. And she said, I believe, in what she said that in the talk, that it had a very high sigma, more than 5 sigma, was the reliability of this other line. Uh, and and the reason that was so much scatter, which is really interesting, because I think this is part of the fun part of this conversation, is the reason there's so much scatter is because they were doing was measuring the two two stars widely separated from one another, so widely separated so that uh, dark matter could have an influence, because dark matter generally has no influence in, say, our solar system. But if you separate stars by light years, then you can begin to perhaps detect dark matter. And that's what was being done. But there's a couple of unknowns, and two unknowns, very important: the eccentricity of the orbit of the stars and the inclination of the orbit of these stars, which creates the dispersion in the data. If you knew that information, then you could, in fact, all the data would line up along the straight line. But you don't, so it doesn't, so it disperses. So somehow or other, they are able to find uh, a way through those dots to come up with a very high probability that the other explanation, the Mon theory, is correct with 5 sigma. Uh, so the question, so 5 sigma is not enough necessarily to convince you if you don't buy some of the premises behind it. Uh, so when people are drawing error bars, and this is definitely a question of error bars, it's a question of whether or not you've sufficiently uh, uh, discovered all the systematic errors in your thinking. But to the extent that you have, and that's of course the thing you don't know, but to the extent that you have examined and know all the things that are wrong with your idea and accounted for them, then you can be reliably sure that what you've seen is true within the error bars that they're showing. Error bars are generally 1 sigma, right? 1 sigma.
Under, got it. Yes, understood. So I think the fundamental question that I'm asking here is, if we take the concept of dark energy and we say that we can't account for what's the value, like 4/5 or whatever of the universe,
Yeah, right, like that.
how are we not at the same place that we were at the end of the 19th century, where people thought that they had it all buttoned up, and then all of a sudden Einstein came in and threw a rock in the pond?
No, no, that's true. And I earlier said that I believe we figured it all out already, and so we won't. I've also said in this room tonight that I believe that we will never get a handle on dark matter, dark energy. And the reason I've said that is because dark energy pervades all of space, and you try to get a portion of dark matter and grab some of it so you can measure it. You know, your apparatus isn't big enough to grab a chunk of it to measure it. So the dark matter will always evade investigation, is what I said. Now, of course,
Hate
I could
that.
be completely wrong.
I absolutely hate that. I absolutely hate the fact that we might conceivably ascribe 4/5 of the universe to an unknown.
Right, but then we would certainly have it. We would be able to describe it, even if we didn't understand it. And listen. There's this little thing called
Sure.
inflation. Have you heard of inflation for the Big Bang?
Well, yeah.
Right? So you can't have the Big Bang without inflation. Otherwise, it's really a nasty hand waving. So what you do is you throw in inflation, and you say, so there was this thing that expanded the universe in incredibly short amount of time, incredibly a large amount, and and then having hypothesized it, it goes on to predict things. So inflation has a predictive value, and in science, if something you hypothesize predicts, then my God, it must be true. Uh, so inflation is real, and so we all accept inflation, and all we're being asked to accept is a little bit of extra inflation for the rest of time. Uh, and we even gave inflation a field, the inflaton, and a field. Uh, I mean, that's crazy enough by itself.
Wait, there's an inflaton?
Yeah, Euro, speak to it.
Oh, God.
Yeah, there's a inflaton
Yeah,
field.
that's absolutely correct. And so, like, you have to imagine the scale of this inflation that we're talking about that, that occurred in a tiny fraction of the second, where the universe doubled and doubled and doubled again multiple times. So you're going from, a relatively small area to like essentially, cosmic universal scales.
Right,
Uh,
and
so
incredibly,
that's explained through the
the, the,
quantum
the, the exponents are ridiculous here.
exact.
Exponents are ridiculous, both in time and space. Right, and now we're only being asked to accept this little extra little inflation called dark energy, and could be part of the same thing. And for that matter, good old Einstein threw in the cosmological constant, which I'm not sure where it stands, but it could arbitrarily be used to explain inflation in the dark energy. Where is Euro? Where does
That's
the
right.
cosmological
So
constant sit?
it's funny because Einstein originally included the cosmological factor because he wanted to include it in the equation so the universe would be steady.
Right,
And then we had the Hubble discovery, and it was like it's not steady; it's expanding. And so at one point he said it was like the biggest mistake he ever made.
right,
But then it turned out later that actually we need that constant.
right. So
Uh,
you made the biggest mistake twice.
he made the biggest mistake twice. Yeah.
Right. Right. But I'm asking you, Euro, is the cosmological constant of Einstein, could it also be dark energy, or is that not in favor these days?
It could be. I mean, the problem is this is a factor that helps explain the expansion of the universe. The problem that we have, of course, is that the rate of the expansion is accelerating, where we would have expected a more constant acceleration. But because it's a constant, right? But yeah, it could still play a role somehow.
Well, it could be a constant that's, I don't know. Uh,
Yeah.
but John Frederick, I think your question is interesting, even to the extent that we didn't answer it. I mean, error bars and all the like. Uh, if you could restate it again, to the extent that we have tried to deal with it uh, in such a way that we can try to deal with it again.
I have a problem is that I
Breaking up again.
sorry, sorry.
Breaking
Check
up
check.
again. Yeah.
Check check. My problem is that I don't know how wrong is wrong. So I don't know what is the order that you're talking about when you say we have to add a little bit to the inflation. How little is that little bit relative to the whole? I mean, what are we talking about? Like, I get that errors compound with distance. So when we start small and we expand to the universe, yeah, you can wind up with the mass of the universe.
I lost most of what you said just now. The it's you actually have to add very little to Newtonian gravity to solve dark energy. You don't have to add a lot. It's a very small uh, factor, I believe. I don't know
like
what it is,
like
but it's small.
percent
Yeah,
wise,
a
like
teeny bit.
1%,
Don't know how much.
more or less.
No, I don't know how much, but it's a teeny amount.
Uh huh.
In other words, it doesn't modify Newton's gravity by much at all. But I haven't seen the equation for modified Newtonian gravity, so I don't know.
Okay.
Anyway, let
We
we
yeah.
we have a
Okay.
we have a new speaker on the table, and it is Evan, uh, and uh, and so I would like to invite Evan to speak.
Oh, hi. Just kind of stopping by, enjoying the conversation. I just had a question for you um, regarding the. I think I came across an article talking about the founding of an ancient, like, ocean floor within the Earth's core. Just wanted to kind of get your take on that. Um,
Explain more. Those words didn't
uh,
mean something together. Ex,
yeah,
ocean floor, Earth's core. I
it's
didn't quite get that.
got it. Yeah, so it's like the Earth's core seems to be made from some ocean, from some ancient materials, or they kind of discovered this crazy article I just kind of came across. It might be something stupid, so I'm not sure if
Yeah,
you heard.
I did see something recently that seemed to be a little stupid, but I didn't read it. But uh, but there is some conversation about the Earth's core or something that I didn't quite register. But I do know that this fact, which is the stuff in the Earth's core, did float down there or sink down there when the Earth was being formed. So the heavy elements like iron and nickel, not to mention the radioactive elements, are sitting down there in the core, and in fact providing the heat that heats, and the radioactive elements are in fact that are down there are providing the heat that in fact is why the Earth is hot down there. But
It mentioned
so
something
ancient,
about,
all ancient stuff.
yeah, mentioned about something about seismic waves, and then that the structure that's holding the core is about 5 times, the size of Mount Everest, and it could possibly, I guess, the core could stop spinning. That would affect something about the.
Yeah, there is. I did see something that mentioned that the core was spinning at a different rate than the rest of the planet, and I know that to be something that's been said, and I don't know if there's any truth to that or any valid science behind it. Uh, I I met it's certainly the realm of people who are alarmists. They certainly would uh, enjoy that conversation. The sun, for that matter, rotates at different speeds at different depths. So it's not like it's an unknown thing. And I think it's also known that Jupiter, you can see the inside of Jupiter because its magnetic field rotates with the inside of Jupiter, and the outside of Jupiter is not rotating at the same speed as the inside of Jupiter. So that's also true, you know. But as far as the Earth's concerned, I'm not sure about that. I haven't really read that.
If
That was really blown up by the populist media. So you're quite correct. The only thing that happened is the inner core rotates slightly faster than the surrounding mantle, and they found evidence that it was shifting about 1 degree eastward per year. And so this got reported as it's stopping or reversing or all this type of nonsense. So not true at all.
I don't understand something. If that's true, and this is where sort of uh, my skepticism steps in, and I go, wait a second here. How could that be? How could the inside of the Earth moving at a different rate than the outside, considering the fact that there's an awful lot of friction? So, could you even remotely try to explain how that could possibly be true, Euro?
Well, my understanding is that they think that the faster rotation is driven by intense heat flows from the core into the surrounding solid inner core, and that this is causing what they're calling drift.
Huh. Hmm.
Like you pointed out, in the sun, the rotation varies depending upon how high or low you are from the equator, and it's pretty dramatic differences.
Right, and also I think there's actually a difference in depth as well, not
That's right.
just in latitude, but also in depth, uh, uh, because sunspots do these weird things, so they can sort of plumb down there. There's also a thing called astroseismology, which is which I don't understand, but you can actually see uh, uh, st- uh, star quakes on the sun, and you can see them propagate through the sun. And not only can you do that for our sun, but it is possible to do astroseismology for stars whose disk we cannot even observe, which I don't understand at all. And perhaps uh, determine. See, stars slow down, which is another thing that's kind of interesting. Stars uh, begin their lives rotating rapidly, and as they get older, they slow down. And so, one of the ways of telling how old a star is, not very accurately, but definitely they do it nevertheless, is to see how slow a star is rotating, which they can do without looking at the disk of the star itself. They can determine that through a little phenomenon called Zeeman splitting, which is the way that the spectral lines separate. Uh, uh, that's a magnetic field thing, isn't it? Oh no, it's a Doppler. It's a Doppler. It's not Zeeman splitting. It's a Doppler. It's a the Doppler lines uh, of the spectrum are spread out, so they can tell how fast the star is rotating, which has nothing to do with the center of the Earth and how it's rotating.
So question on that. Stars don't have a phase change from the core outwards, or do they?
No,
They're assumed to be a plasma all the way out.
yeah, they do, but there's definite changes. For one of the things that is not terribly obvious, uh, but is true, is that stars have a convection zone and a irradiative zone. And depending upon the size and age of the star, those zones vary in size, and, depth, and properties. For example, our sun has a convective zone in its outer layers, hence sunspots. They prevent the convection, and because of they prevent the convection, they are dark. And where the convection is not prevented, it's bright. So that's what makes a sunspot. So the surface of the sun is convective. Inside, in the center, it's radiative. So the heat is transmitted by radiation, whereas the outer layers of our sun, the heat is transmitted by convection, which is all very interesting, I think.
That that's that is very interesting. And when I relate it to the Earth, I'm thinking if discrete layers of the Earth are different states of matter, we've got a solid core, we've got a liquid core, we've got a plastic mantle, and we've got a solid crust.
Right.
And each one is rotating at a slightly different speed. So their centroids don't necessarily align.
I'm going to go with uh-huh. I don't
So
know. I don't know this stuff.
so there's not an actual center of the Earth because each different part of the Earth has a different center.
Are you asking or saying or
I'm
declaring or just?
asking, I'm
I
asking,
don't know. I
I'm
don't know.
throwing that out there saying, is this bullshit or not? Because to
Well,
me,
it's not
if it's a
it's a
bunch of different hula hoops,
it's a worthy hypothesis, which I have no idea whether there's any truth to it.
because I mean, riff with me. I mean, if they're different densities and they're different states of matter and they're different dimensions and they're rotating at different speeds, how are their centroids the same, considering that each one is essentially, as you said, what was it? An obloid, no, a something
Oblate
spheroid,
spheroid.
an oblate spheroid. So how can 4 or 5 different oblate spheroids of different densities and states of matter have the same center?
I don't know. I really don't. When it comes to the Earth itself, I really don't know. There's a certain field of knowledge. It's called geology,
Yeah,
and I don't know anything about it.
heard. But
It's
our
it, yes.
but our observational instruments are based on understanding where they are in space, and where they are in space is relative to the center of the Earth.
Yes, yes. I think the Earth has a well-defined center.
Okay,
I think that's true,
within
despite
within
the fact
Six
that it's an
Sigma,
oblate spheroid.
within 6 sigma, we know where the center is.
Well, let's put it this way. Uh, I would say that the center of the Earth is known to within a few meters, plus or minus a couple of meters, within 6 sigma. Yeah, plus or minus.
Okay,
When they say plus or minus, it means within 1 sigma.
okay,
That's what plus or minus means,
okay. And
right?
so, taking that into account, if you multiply that out by however many light years you're looking,
Yeah.
You don't that error, that multiplication of that error doesn't really pose any
Oh,
problems.
no, no. Well, let's say we're looking to understand the motion of the planets around the sun, and let's say that we want to predict where the Earth will be and the planets will be in 1 million years. We can do that. If we try to do 100 million years, we can't. And the reason we can't may have some. This is where I'm going to speculate here. It could have to do with the non-roundness of the planets, the obliqueness of the planets. It could have to do with the fact that we don't know where the center of Jupiter is to within a sufficiently small distance so that we can predict where it's going to be next 100 million years from now. That's called chaos theory. And I think it's more like that, that given we don't know the starting constants to begin with, so when you don't know these, like the butterfly thing, if the butterfly flaps its wings on the other side of the earth, it could cause a hurricane on this side of the earth 2 weeks later. That's because we don't know the initial conditions. We don't know the initial conditions of a solar system. I don't think it's because we don't know where the center of the earth is. It's because we just don't know anything to that precision. We do know the center of the Earth, but we don't know where Jupiter's center is, because it's like, maybe within a kilometer, you know, or maybe within 100 meters. But that's enough to throw off the calculations for the next 100 million years. So I'm not sure what you're saying.
That's wonderful. Thank you.
Can I add a comment real
I love
quickly?
tolerances.
Yeah, please do.
Yeah. So the non-coincident layer centroids from the different layers actually help puts constraints on the models for determining the center.
Oh, great.
Explain more.
Yes.
Explain more.
Yeah. So he quite correctly pointed out that you have these different layers of the Earth, right? And
Right.
they're rotating at different speeds. So they do have separated centroids.
So this is true. Okay, go
Oh
on.
yeah, that's true.
I did not know.
Okay, but what happens is like our geophysical model incorporates this effect, and so because of that, we're able to determine the Earth's center with a relatively high degree of accuracy. So we're talking about sub-kilometer level
Yes.
of
Yeah.
accuracy.
So how accurately do we know where the center of the Earth is, given that you know all this?
It's sub-kilometer. It's within a few hundred meters. Because
So,
because of these dynamics, it does change, right? So you have we have satellites, for instance, which help us make gravity measurements,
yeah,
and the core rotation is very important because that means the dynamical center is transitly shifting by meters with time due to the Earth's slightly non-hydrostatic figure that you talked about.
really, this is all interesting to me.
Yeah, yeah, yeah. You can look at the gravitational pull of like the ocean and atmosphere masses, for instance, and the subsurface density and homogenies, and so those all contribute to small uncertainties. But I mean, it depends on what level of accuracy you're asking me. I would say that we have a very good understanding, but it's not.
I would have thought that the center of the Earth was known to within centimeters rather than, as you say, hundreds of meters. It's
That's
interesting.
my understanding. I don't know that we have more precision than that, unless there may have been something new that has come up. But as far as I know, because of all these dynamics going on, there's various geodetic modeling that they use for these gravity field measurements that locate the center.
Listen, Euro, I want to. I'm going to sort of end more abruptly than usual because I have to get up in the morning. But let me ask you just a personal question. Where do you live, Euro?
So I live in Paris.
You live in Paris.
Yeah,
Oh, so this is very early in the morning for you.
it's almost 7 a.m. right now.
And what time do you normally get up?
Well, it varies. I'm not very good at keeping
No,
a
no, but
consistent.
I just want to tell you that of the people who have, of the experts who have populated this room with me, you're one of the very, very best that I've ever had.
Oh, that's very kind. I thought your answers today were phenomenal. I mean, you nailed so many topics, so many different fields. It's just like watching a baseball hitter just knocking them out. The only thing I would say is like, you really firmly believe that we're never gonna find out about dark energy. The only
Yeah,
thing I would say is, that was said for a long time about gravitational waves. Even Einstein, who had predicted them, said
yeah,
that, well, we'll never actually detect them.
yeah.
And
That's true. That is a good point. That's a
yeah,
very good point because we actually it took being able to measure distances that were a very small
exactly.
fraction of a
So
proton, before we could
exactly so
before we
small. So the thinking for the longest time is, well, it could be true, but we'll never actually detect it. And look, in 2015, I think it was, we
yeah.
actually did. So I don't like to say never, but I understand what you're saying. The
Yeah.
difficulty.
But I just want to know how I can get you to come to this room every time I do it. I,
I
I,
don't
I
know
mean,
when you have it. I just find it by chance, and I
well,
and I,
I do it every week. It starts at 11 o'clock in New York City, which is 5 hours. So it's 4 o'clock in Paris. Uh, right,
on every Tuesday.
every Tuesday.
Okay, well, maybe I could actually remember that then. Yeah,
Right.
I
For
just
it.
always find it by chance, and as soon as I seen the title, I love it because you run a great room. And do you remember? I think it was last week. Um, you had to leave, and you left a few of us in the room,
Yes, yeah, I did that. Yes.
and there was one person in the room. Unfortunately, I wasn't looking at the screen, so I don't know his name, but he posted a question about ChatGPT,
Uh huh.
and he was saying a certain type of question. I don't know if you were here for this because you were leaving.
Yeah.
He said a certain type of question it's impossible for ChatGPT to answer because he said it had branched inferences. So I asked him if he could copy the exact question and wording in
Hmm.
the chat, so I could test and get it right. And I gave that question, copied and pasted directly from the chat.
Uh huh.
ChatGPT came up with the right answer instantaneously, and he
Really,
said it would be impossible for it to solve. So I was
it's
like,
possible that ChatGPT is being tweaked.
"Well, this is what I think." But he was saying like the very nature of the question would
It
mean
is.
that it's impossible, but apparently not.
Uh
Uh,
huh. Yeah, no, I, that is an area of non-expertise. I'm at the level of being a fan. I'm a fan of ChatGPT, and I worry about my daughter, who needs to learn about it because she better get expert on it because our world is changing. She's making a living uh, as a entrepreneur, and she better get on the stick with ChatGPT because it can help entrepreneurs. And so, but I'm not any longer an entrepreneur, so I don't need to know. I can just play with it. Uh, but you got to come next week and every week thereafter if you can. I don't know what do you do for a living?
oh, I work in IT now, but like I said, I used to work at an observatory, and I was involved in a team. We were doing all types of solar analysis. So when you started talking about um, the different techniques they use in terms of oscillation spectra analysis and how that helps determine the pulsations and the different internal vibrational modes within star due to pressure variations and buoyancy uh, forces. I was like, oh my god, yes. It was very,
Right.
very interesting. It's kind of analogous to like sound waves, I would say, to laymen. But you said something else I thought was really significant about truths that we're not going to be able to prove or understand. And I
Yeah.
was listening to a data.
Godot. That's his name. Godot.
Yeah, I was listening to a data scientist. I think he's out of Australia, and he's been following like all these AI bots like ChatGPT and stuff. And he pointed out that on a theory of mind test,
Uh-huh.
uh,
Yeah.
the bot got a perfect score. So
Yeah. It
so
does.
better than any human.
The Turing test is dead.
Yeah. So he raised this point. Since it's better than our tests, how do we know how much better it is? Because like we don't have any way to measure it because it's outside of our, like, is it just at the highest level or is it even higher? And then he said, what's going to happen in the future when it starts telling us that there are certain truths or things that it determined and we don't have a way to verify it? Like, do we just accept it, or you
Oh,
know,
oh God.
you
Uh,
know, you
uh,
can see the problem, right? I mean,
yeah, I'm glad I'm going to die soon. I mean, I don't, I wouldn't want to. The world in which this sort of question is reasonable is going to be really difficult to live in. Jack is my son-in-law. He's in the room on the stage. I was just saying that you and Tara, my daughter, need to get real expert on ChatGPT and all these AI things in order to compete in the entrepreneurial world in which you live. And I'm glad I don't have to do that. But ChatGPT and those AI bots are really what people need to be expert in order to compete these days. It's definitely true. Uh, and, and and for that matter, my daughter owes me I've asked her to describe her business, and then I will become an expert in ChatGPT to get ChatGPT to tell me ways that she can market her business. And she has not as yet done so to send me a synopsis of her business so I can ask ChatGPT to weigh in. Because if you ask ChatGPT for ideas, it really has ideas. And if you hone down on those things, it keeps getting better and better at things. If you object to what it said, it will recorrect itself and go elsewhere. And so I've done a little bit of that, and it's fun. But I think, and I know a friend of my daughter's who works at HubSpot uh, uses ChatGPT. The people under her use ChatGPT to do their work so they can be more productive on a daily basis with what they're otherwise doing. So it's the tool of the future. You don't even have to trust it because you can trust yourself right now. But you're suggesting that in the future we might have to trust it, and that's where I say I'm happy I'll be gone by then.
yeah, that was the question that this scientist raised, and you're quite right. Like today, we can verify and see, like, does it make sense, or it doesn't make sense. But what happens when it starts talking about things that are so advanced that we don't have a way to do that?
Yeah,
So,
it's just a large language model. Come on, give us a break.
can I ask a thing? Because yes, it's a large language model, but for us out here on the outside looking in to the scientific process, who are not necessarily, participants, but astounded admirers. My question about how do you know if somebody's BSing you?
Yeah.
Well, the scientific community error checks itself because of consensus.
Yes.
And we have essentially, as Wikipedia puts it, a consensus truth.
Yes.
So, how many chat GPTs are there right now? How many AIs do we actually have which have different models?
Oh God, no.
And are we going to have a
Oh no.
consensus
Oh
truth
no.
between the AIs,
Oh no.
given that they are simply better, not necessarily better scientists, but faster ones?
Okay.
So, are we just transferring the scientific process, the scientific community, to a competition between AI arriving at a consensus truth?
I don't want to even think about what you just said. And because it is late, and because I do have
Yeah.
to, I have to drive to New York City tomorrow. I'm not in New York City, and I have to drive there, and I have to be there by 12 o'clock my time, and leave at 9 o'clock my time. and so that means that I need to get 8 hours sleep my time, and so I wondered, Jack, Jack is my son-in-law, and he will never rest unless I give him the stage, so that otherwise he'll badmouth me for the next week. So Jack, it's your turn, or maybe he's not here. Normally, by the way, uh, 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 when and I am going to end the room soon, but I just want to let you people know that for the first 2 years of Clubhouse, Jack lived in Istanbul, where the time delay was 7 hours. So my grandson would get up, and starting at the age of 2, he would always close the room by telling me, "Go to sleep, Grandpa." But now that he's 4.5, he's no longer interested in saying that. He can't be programmed to say it anymore. And furthermore, it's too early for him to be awake, I think. So maybe if you're here, you should tell me to go to sleep. Could you do that if you're here? He's not here. Okay. Because you know what he does? He gets up in the middle of his night, turns me on, and then goes back to sleep. So look at, I am ending the room now. It is, I am Laird, actually Laird Whitehill, uh, and as Laird Whitehill, I recommend that you check out my YouTube videos under Laird Whitehill, so you can see 42 hours or more of me doing this, in which I actually lecture, and I lecture about astronomy, and you can see the links that I use to lecture in my lairdwh.com, and you can see a link to my YouTube videos on lairdwh.com, and you can like my YouTube videos, and I appreciate people just turning my YouTube videos on and letting them run all night, because I get longer views that way. Most people average 6 minutes on the average of my YouTube videos, so I would forgive you to watch no more than 6 minutes. But I would enjoy you all coming back next week, at Tuesday, 11 o'clock Eastern Time. And hopefully Clubhouse will survive another week before it runs out of gas. It certainly looks that way to me. But I hope to be here next week to continue doing this, because this is what I love doing, and I appreciate your help. And Euro, if you can possibly come, I would appreciate it. You are really, because you're informed about the things that I'm informed of, and yet you're working in a different field. Well, I worked in IT for 25 years, so we're kindred spirits.
We are kindred spirits. And the last question about using multiple computers to check each other, NASA does that all the time, by the way.
Yes, it does.
Particularly in launch vehicles, they'll have multiple computers that, there's no AI necessarily involved, but they're used to test to make sure that they're getting the same results. It's really important for launch vehicles and spacecraft design.
Right, and the Apollo
And
vehicles did
weather
that.
models.
Right. Yeah, with them all. And the Apollo vehicles did that, and they had 5 computers on board.
Yeah, exactly. Five computers, and they have to get consensus before they take a decision, because errors could creep in somewhere. And it was also part of 2001: A Space Odyssey, when the HAL 9000 computer on board reached a different conclusion than its twin on Earth. That raised a lot of concerns.
Right. That was, I thought that was overdone, but it had appropriate for the movie.
But yeah, it's
Uh,
dramatic, but but the
right.
idea, yeah.
Right. All right. So I
Very
appreciate if you
excellent.
all come back next week. We've just barely touched the surface of astronomy tonight, and there's so much more out there in the universe to discuss than we have tonight. So this, and there's the good deal of it I understand and can explain. And I thank you for your compliment, Euro. I do truly appreciate that. With that, I think the room is about to end.
Well,
And
I'm very envious of you because you have the Carl Sagan experience, and I can only even just imagine, how great that must have been.
Yeah, it is and was. And of all the things that's ever happened in my life, I feel most guilty about not uh, being there for Carl Sagan as much as he was there for me. So we'll talk another time. I'm going to end the room now. It's going to count down from 10 to 0, and I'm ending at that point. And you can count down with me or not, as the case may be. 10, 9, 8, 7, 6,
6,
5,
5,
4, 3, 2, 1, 0.